quantum mechanics is used to describe really the universe at the atomic scale, how atoms work. So what we often see from quantum mechanics in our regular day-to-day lives is actually sort of the average of quantum mechanics working, which is what this Newtonian physics really kind of is. But there is some quantum mechanical phenomena which we can observe on the macroscopic scale, and one of those is actually superconductivity. Superconductivity is when a material has zero electrical resistance. Now, most metals will conduct electricity, and if they do, they'll have some kind of resistance. Universally, they'll have resistance at room temperature. Resistance is when electrons bump into impurities inside the material or the walls of the material itself as they're passing through the material, such as a wire. When the electrons bump into those impurities or the walls, they generate heat. So as electrons flow through the wire heats up so that some of the energy that might have been used to generate light for like a light bulb will ultimately become heat. Conducting materials, like metal, will typically have a resistance no matter how cold I get it, even if I get it basically down to absolute zero. But that's not true of all materials. There are some materials where as you're getting colder and colder, you still have some finite electrical resistance, and that at a certain temperature, that electrical resistance completely disappears. And those materials are called superconductors. There are two main types of superconductors. The first kind of superconductor is a low TC, or low transition temperature superconductor. And these superconductors have their transition point where they become superconductors at a very low temperature, typically around liquid helium temperatures, which is 4.2 Kelvin or minus 435 degrees Fahrenheit. That's really, really cold. And these materials tend to be a little bit more simpler, like lead. They tend to be sometimes elemental. And we understand how those materials turn to superconducting, where basically the electrons begin to act like a superfluid inside of the metal, and they actually will flow freely without any resistance. In short, the electrons, which are a kind of fermion, meaning that they have a magnetic spin of 1/2, when the superconductor gets cold enough, the electrons will pair up with other electrons, and that pair will be a boson, which has a magnetic spin of like 1 or 2. And as a boson, it will actually be able to be a superfluid and behave like a superfluid. And so it will flow through the material without any resistance. The second kind of superconductor are these high TC superconductors, or these high temperature, transition temperature superconductors. And what's going on there is that these guys tend to be more like ceramics, and they tend to be more complicated. Ceramics are like glass or something like that. And they're not so easy to understand. We don't understand them as well. So one example might be YCBO, which is yttrium barium copper oxide. It's this complicated material that tend to be, because of ceramics, they tend to be more brittle and not nearly as strong as the lower temperature superconductors tend to be at. Their transition temperatures is actually much higher. So it's around liquid nitrogen temperature, which is 77 degrees Kelvin or minus 321 degrees Fahrenheit. And although that sounds really cold, that's a lot easier to make liquid nitrogen than helium. Unlike low temperature superconductors like lead, which follow BCS theory, the high temperature superconductors at around 77 degrees Kelvin, we don't understand those nearly as well. That's actually a main point of current research, is understanding how that superconducting transition state happens and why they're superconductors really at all. Superconductors have some very neat properties to them. One of those properties is that magnetic fields will not penetrate or go inside of a superconductor. When you bring a magnet close to a superconductor, small currents will form on the surface of the superconductor called eddy currents, and they will generate magnetic fields which will directly oppose any field that's even near that point on the surface. Which means that if I put a magnet above a superconducting puck, say YCBO, then that magnet will actually float above the superconducting puck if the superconducting puck is cold enough. This effect is called the Meissner effect. This video was made in the Sydney Boys High School in Sydney, Australia. And here you can see they're just pouring liquid nitrogen on a YCBO puck, which is black, and then there's a gold magnet that's above it. And you're watching all the bubbling that's going on as that is liquid nitrogen evaporating and cooling off both the magnet and the superconducting puck. What matters here is that the superconducting puck is cooled. The magnet itself, it doesn't matter. But as the superconductor cools, it goes through a transition from a normal state into its superconducting state. And when it does that, the magnet will lift up, just like you've seen. and kind of float up there. Now you see it floating, hanging in the air, and what you can do is you can actually spin it with tweezers, which they've done right there. This is such a very neat effect because it's very difficult to create this stuff artificially. So we do have levitating tables and stuff like that that we can do artificially, but this is done naturally, and it's always perfect. It's always going to levitate any magnet we put on there, independent of the geometry, and there's no electronics that goes with it. So I think that's super cool. Superconductors also have a lot of practical uses. One of the main uses of superconductors nowadays actually is to make magnets, very large, powerful magnets. Stuff for MRIs, or magnetic resonance imaging. The magnetic fields necessary for these MRIs has to be enormous. They have to be on the order of what's called a Tesla. Now that's 1 Tesla, doesn't sound very big, but the Earth's magnetic field is actually 10,000 times weaker than that. So we have to have a magnet that's going to be 10,000 times stronger than the magnetic field of the Earth. If we were to try and generate these kinds of large fields, and not just large fields, but large fields over large areas with traditional conductors like copper, it would take way too much energy. These copper wires would get way too hot and be completely useless. But with superconductors, when I get them into their transition state and I dump all this current, I put all this current through the cables, they don't heat up at all. And so we're able to maintain these extremely high fields, these extremely high currents without having to worry about cooling off what would be a monstrous amount of heat with copper wires. Ultimately, superconducting wires is what makes the MRI machines that we have today even possible. Thank you so much for watching my video. I have lots of others. Please like and subscribe for more content. And everybody have a wonderful day and a wonderful week. Thank you. Bye-bye. This has been a production of Van Cleve Scientific. Please like and subscribe for more content.